Welcome to Module 6.1. In this module, we'll begin our conversation about mathematical logic. This is an old subject, and it has deep intersections with philosophy. It's still contemporary. People are still trying to make sense of some of the contradictions of mathematical logic that arose in the late 19th century and early 20th century. A few names, if you're interested in these types of things, are Cantor, Gödel, and Wittgenstein. I personally don't have much of a taste for this subject, but some people find it very, very interesting. We'll look at just a few basic terminologies and concepts that will be important for the CLEP exam. And if you have an interest in this thing, you can certainly go into more detail in your own studies. The idea here in mathematical logic is to formalize notions of truth and falsehood. We consider sentences, which is anything that can either be said to be true or false. So for example, I am standing is a sentence. There is a door in this room is a sentence. The sky is green is a sentence. We don't necessarily care whether the statement or the sentence is true or false, only that it has the quality of either being true or false. We say that a sentence is consistent if it is not self-contradictory. What would be an example of a self-contradictory statement? Something like the following. The sentence could be, it is Tuesday, and it is not Tuesday. So a very kind of fundamental breakdown in what we kind of understand truth to be in logic. One must keep in mind that when discussing truth, it doesn't necessarily relate to its content, only to basic logical principles. Just going back to this sentence here, it is not true, or because it is self-contradictory, not because of anything to do with the day of Tuesday. We can also discuss statements. These are our basic atoms of logic. We use statements to build concepts. Okay, so we will typically use the notation A, B, and potentially C, and so on to represent statements. We'll actually wind up forming an algebra out of statements, where we can combine statements, link them in various ways. So a little bit of notation that will be important for the CLEP exam. Keep in mind that there's actually overlap with the notation here and the notation that was used in our modules on probability theory. We say A with this downward-facing wedge to denote A or B. So this should be compared to A union B to denote the union of events in probability theory. Similarly, we have an upward-facing wedge, like this, to denote and. And this should be compared to A intersect B to denote the intersection of events in probability theory. And then this twiddle here denotes not. So taking a statement and saying not that statement. So for example, if A is the statement, the cow is white and black, not A, or twiddle A, would be the statement, it is not the case that the cow is white and black. So a few kind of cool remarks here, which is how negation interacts with and or. So if I had the statement not A or B, that's equivalent to the statement not A and not B. Similarly, the statement not A and B is equivalent to the statement not A or not B. These are worth thinking about. If I have something where I am interested in either A happening or B happening, what does it mean if neither of them happen? Well, it must be the case that not A happens and not B happens. And that's basically the derivation of the first formula. The second is similar. If I need A and B to happen, how can that fail? Well, either A cannot happen or B cannot happen. Hence the second formula. Some more notation. When we're given two statements A and B, we can write the conditional statement A implies B, or if A, then B. So as an example, let's say A is the event, it is raining. And B could be the event, the ground is wet. Then the statement A, arrow B, would mean if it is raining, then the ground is wet, which seems reasonable, though we're not evaluating whether it's true or false. But that is one way to combine statements in mathematical logic, is through this conditional operator. These are very important, understanding if-then statements. So we give names to related statements, which will be potentially important on the CLEP exam. We define the converse of the conditional A implies B to be B implies A. So in our case, the converse of if it is raining, then the ground is wet is the statement, if the ground is wet, then it's raining. The inverse is when I negate both A and B. So the inverse of A implies B is not A implies not B. So in this case, that the negation, or rather the inverse of our conditional would be, if it is not raining, then the ground is not wet. We will establish in a moment that the converse and the inverse do not have to have the same logical truth or falsehood as the original statement. What does have to have the same logical truth or falsehood is what's called the contrapositive, which is somehow a combination of inverting and conversing. So this combines inverse and converse. So the contrapositive of A implies B is not B implies not A. So if our original statement was, if it is raining, then the ground is wet, the contrapositive would be, if the ground is not wet, then it is not raining. These can be shown to be equivalent, that A implies B is equivalent to not B implies not A. And this is a foundational observation and is the basis behind proof by contradiction. Which is an important theoretical mathematical technique. Okay, so let's look at a specific example. Statement A is, today is Thanksgiving. Statement B is, today is a Thursday. What we'll do is we'll try to interpret the statement A implies B, and then we'll also state the converse, inverse, and contrapositive of this. So what's the interpretation of A implies B here? It would be, if it is Thanksgiving, then it is a Thursday, which seems like a true statement. Let's look at the others. For the converse, we write B implies A, and now we interpret. This would say, if today is a Thursday, then it is Thanksgiving. Which is not true. So we see that it's possible for the original statement to have truth content, but the converse not to. So they are not equivalent. Oops. The inverse would be not A implies not B, which we now interpret. If today is not Thanksgiving, then it is not a Thursday. Which is also not true. It's very possible for today not to be a Thanksgiving and for it to be a Thursday. So keep in mind that the original statement is not logically equivalent to the converse or the inverse. It is logically equivalent to the contrapositive. So let's write that out. This would be not B implies not A. And in words, if it is not a Thursday, then it is not Thanksgiving. So we have discussed how a logical conditional is not necessarily equivalent to its converse. That is, A can imply B, but it is not necessarily true that B implies A. In the special case that this does happen, we have what's called a biconditional, or if and only if statement. So this is a statement of the form, A implies B, and, right, this wedge here means and, B implies A. Sometimes this is denoted in the literature as a double-sided arrow, to mean A implies B and B implies A. Okay, so what we'll do now is we will look at three different logical statements, and we'll combine them in various ways and try to interpret them. So the first statement is today is in April, so a day in April. The second statement is today is a Tuesday. And the third statement is today is a Wednesday. So let's interpret these. A, upside down wedge B. Well, this is an or, so this means today is in April or a Tuesday. Here I have a combination of things. So this means in parentheses, today is a in April and is a Tuesday, or today is Wednesday. So another way of thinking of this is that statement says today is either a Tuesday in April or today is a Wednesday, with no condition on it needing to be in April. The next one will be similar. It will be today is in April, or today is a Tuesday and today is a Wednesday. Now, if we were asked what is the sense in this statement, we would say, well, the second part's a little weird, because the second condition, or the second possibility, is today is a Tuesday and a Wednesday, which isn't possible. So the overall statement, which is today is in April or today is Tuesday and Wednesday, really is equivalent to today is in April, because it's not possible for it to be both Tuesday and Wednesday. Okay, so another example. This is saying today is in April, or today is Tuesday, and today is Wednesday. Which again, we could say this whole thing is equivalent to today is in April and is Wednesday, because it's not possible for it to be Tuesday and Wednesday. So it can sometimes be helpful to think a little bit about these conditionals beyond just the obvious interpretation. How about this? A implies B would say that if it is a day in April, then it is Tuesday. Now, we know that this is not true, but we're not really interested in determining the truth and falsehood. We're just writing down logical statements. Now we're getting a little bit tricky. Not C implies B. What does that mean? That means if it is not Wednesday, then it is Tuesday. Which also doesn't necessarily square well with our logical intuition, that would not be a statement with truth in it. Lastly, we'll look at C implies not B. What does this say? This says if it is Wednesday, then it is not Tuesday. And we believe this. This is reasonable. Okay? So this is sort of an introduction to the type of logical statements you'll be expected to understand. For the CLEP, you certainly want to be able to parse or be able to read and understand how to combine statements through and or, also reading conditionals through the arrows, understanding the notions of inverse, converse, and contrapositive.